So we're going to get started with 15.4, which is integration of polar, cylindrical, and spherical. I'm just going to go ahead and skip 15.3 because the only thing in that section is we're just like, can you do a triple integral? And if you can't by now, then I don't really know how useful this will be for you. But so 15.4 objectives. We have double and triple integrals in polar, cylindrical, and spherical units. So what that means in terms of changing your variables from rectangular x, y, z to polar, cylindrical, and spherical is you're pretty much just going to use your x equals cosine, or x equals r cosine of theta, y equals r sine of theta, and z equals d for cylindrical. And then for spherical coordinates, you just have x equals rho cosine of theta sine phi, y equals rho sine theta sine phi, z equals rho cosine phi. So like, I know it's like a lot to remember, but if you can convert from rectangular to cylindrical, which we all should be able to do, if you just remember that r equals rho sine phi and z equals rho cosine phi.
Draw the triangle.
It's a dumb triangle.
No, it's awesome. Just remember the triangle.
Oh, well, you can draw the triangle on that board if you want.
No.
You should be fine, because we know that like x equals r cosine theta, y equals r sine theta. That's easy to remember. You can just plug in this for r, and you're good to go with spherical also. So that should be nothing new and nothing difficult. The only thing that gets kind of hard is determining like what are the bounds of integration. That's where like most of us lost points on that 15.3, 15.4 quiz. So for polar, it's actually like really straightforward in terms of you're only dealing with an xy plane, or you're only dealing with a two-dimensional space. And you know that your radius is just like how far you are from like the origin, and you're just gonna like sweep across it. So, and like the angle that you sweep is theta. So I'm not gonna spend too much time on that because that should be really straightforward. For cylindrical, it gets a little more complicated because now you're in three-dimensional space. So what that means for your bounds is you're still going to go from like whatever theta you start with to like whatever theta you want to end with. The same like you're sweeping out an area. And you still have the same like r bounds. Your radius is still from a certain radius to another radius. So the only really added layer to cylindrical coordinates is that now you're considering you're going up and down along the z-axis, and you want to enter the region and then exit the region, and that's going to coincide with your bounds. So if you see here, this z1 corresponds with this lower like part of whatever shape this is, and this z2 is the upper z bound. Does that make sense? Are we all cool with that? Awesome. So spherical, like I said, this gets more complicated. Theta still signifies what, you know, like sweeping an angle out from the x-axis, going along the y-axis, and going around. And they can take on values from 0 to 2 pi. Rho is just kind of like your three-dimensional equivalent to your radius, where instead of just moving along a radius along the xy plane in two-dimensional space, you're just going like, you can go like up a certain degree.
It's a distance from the origin.
Yeah, so like, but it's like in 3 dimensions. So that's fine. Phi or phi, I'm not really sure how to pronounce it, your angle of declination, that's like the only new thing that really comes out of spherical coordinates. And that's just going to be your angle of declination from the z-axis going down to wherever your region starts and ends. So if you think about spherical coordinates, it's called spherical for a reason because you're integrating across like a chunk of the sphere. You're always going to be able to carve out what you're trying to integrate out of the sphere. So something actually really useful that, yeah, I got your email, thanks, the test. Something really useful for spherical, cylindrical, and polar is, if you notice, your bounds can take on variable values. And like we've seen that in past homeworks in the web works. And when you're in a situation like that, you just have to like do the integration like you normally would. But something really useful comes about if your theta bounds, your phi bounds, and your rho bounds are all constants. Then you don't have to go through like each integration step by step. You can just do each individual integration and multiply by each other. Because if you think about what you're doing with each of these integrations in this like multiplying way, when you do the theta integration, you're getting this like first little leg of like how far you moved in the like theta wise, sweeping across from the x to y axis. And then when you integrate by phi, this is the like up and down side that you're getting. And like you're multiplying that together to get this space. And then when you multiply by rho, or the integral of rho along your bounds, what you're effectively doing is you're multiplying by another dimension. So that's how you get this like three-dimensional spherical volume. So that's all for 15.4. 15.5 is pretty much taking all of the integration techniques that we've learned about double and triple integrals and applying that to, you know, instead of just saying, what is the surface area of this like spherical chunk, like let's actually start giving those variables meaning. So like first and foremost, the easiest kind of question they could ask is, you know, find the total mass of this shape that's bounded by these regions. And pretty much all you really, the only like new thing for this application is instead of having f of xy, instead of having some two-dimensional function that like doesn't mean anything, we're changing that to rho of xy. And this rho isn't the same rho that we use in spherical. It's simply rho, like that's just what it's called for a mass density function. So now instead of having f of xy meaning nothing, we've ascribed it to a density that goes along with our integration so we can find the total mass. So the next kind of application is center of mass, where for a given region, you can have, you know, all of this space, right? This is just kind of like a two-dimensional like simplification, but each one of these little like points on this in this region, it's going to have an associated mass with it. That's what I was saying before about like the functions that we're integrating. Now they have a special meaning to it. So we know with all things like integral related, we're adding stuff up. And so if you think about center of mass, of like what is center of mass conceptually, it's a weighted average. It's where is all the mass located in an object, in a region, in something. So it makes sense that the center of mass should be like some kind of location of like where, what point of mass are you talking about, and then also how much mass is it, and then it should also be taken over or divided by the total mass to get that weighted average. So if you think about like what the moments of like the y and x axis equal and what the total mass equals and how that fits in together with like center of mass of some crazy region, like it should all make sense. That the moment about the y-axis, so here's your y-axis, is going to be the distance from the y-axis, which is that, you know, piece I was talking about where are you locating your mass, where is this point of mass you're investigating located, times like how much mass does it actually have. So that's where you have your mass density function, rho of xy. That's where it comes back into. And then to find the y center of mass, you're taking this moment about the y-axis, and you're taking that and dividing it by the total mass of the entire region to get that weighted average. Do you guys have any questions on that? Just center of mass in general? Well, so I'm just going to talk through all of these kind of conceptually first, hit the objectives, and then we're just going to start like doing practice test problems like over and over again until we get tired and leave, which will hopefully be before 8 o'clock. But yeah, so that's center of mass. So if you think about center of mass in just like layman's terms, I think it's really easy to think about it in terms of just distance. So x being the moment about being the distance from the y-axis times mass. So if that works for you, that's great. And if you can see that in the formulation, that also helps a lot in terms of like you're not memorizing another integral formula because we already have like 10 of those. So if that helps, that's great. It's kind of a nice segue into moments of inertia, which I don't remember if maybe specified if that would be on the exam. But for moments of inertia, it's just instead of the mass times the distance that you're integrating, it's the mass times the distance squared. And you see that in the formulas. I don't know how you guys can see this. What's up?
I don't think back section.
Oh, really?
Yeah.
Oh. Well, if you're in back section,
three
sorry.
dimensions.
Of what?
Like finding the center of mass of a two-dimensional object, which is above that.
Yeah. But who here is in back section? I'm just Manny. Alright, well, that's Manny after that.
Yeah.
But for moments of inertia, like it makes sense that if you want to find the moment of inertia about the x-axis, then you're going to have y is going to be your distance from the x-axis, and all you're doing is you're taking that y value and you're squaring it. And you know this is rho of xy, your mass density function, so it makes sense that like mass times the distance squared, sorry, is the inertia. Like we haven't had like web work problems like that, so I'm just gonna kind of leave it at that. Hope that's cool. Okay, so that's pretty much 15.5 in a nutshell. If we look back at the objectives, the total mass of 2 to 3-dimensional region, I just talked about that. The center of mass of laminas. So for laminas, all that means is that your rho of xy, so rho of xy, like that could equal something like x plus y squared minus 2 where it has variables in it. But if it's a lamina, that means that the rho of xy is just some constant. That the density isn't changing from like this point in the region to this other point in the region. Center of mass for 3-dimensional objects. So let me go back to that real quick. So center of mass in 2 dimensions is pretty straightforward. But when you get to 3 dimensions, the only thing that really changes is that you have like a lot more integrals to do. Instead of saying like, let's just find the moment about the y-axis, let's just find the moment about the x-axis, and like those are the only 2 things we care about. Now we have to consider the x center of mass, the y center of mass, and the z center of mass. And these moments are no longer the distance from an axis, it's a distance from the xy plane, from the yz plane, and from the xz plane. But the formula like is still the same, which is really nice. If you look at the moment about the xy plane, and if you think about this visually, like here's your z-axis, this is your x-axis and y-axis. The xy plane, the distance from that is just going to be z, because you're just going up and down, right? And that's reflected in the formula. So you have z times your mass density function. So mass times distance again shows up. So I actually, for the test, because there are like 3 triple integrals and like a 4th integral for total mass, and they're all like triple integrals and really long, I don't think that you'll just ask a straight up find the center of mass of this 3-dimensional volume, because there is so much like computation involved with it. But what is possible is to just say set up the integral. I know we have like quizzes like that, so that is definitely fair game. But I think that an added layer of like difficulty would be to have this volume symmetric about some axis, or like symmetric in some way. We know from like Calc 2 even that when you have a region and symmetric about something, that you don't have to do all of the moments or everything, because you know that like, for instance, you know that this parabola is symmetric about the about the y-axis. So that means that you know that your x center of mass is just 0. And so that pretty much you just like cut your work in half. You only need to find the moment about the x-axis to find the y center of mass, and it'll be like somewhere around here. So for 3 dimensions, it gets kind of like harder to visualize and think about like what does like 3-dimensional symmetry look like. But so what I was talking about before, where you have your xy plane, and z is the unique variable, z is like the up and down movement, and then if you have your zy plane, like you can only move along with x, so x is now the unique variable. We did some of that when we talked about like parabolic hyperboloids and stuff like that. The same kind of like mindset applies to 3-dimensional symmetry, where if you have a function, wait, no, I shouldn't be rho. Oh, sorry, let me backtrack. When you have variable density, you need to make sure that your density is also symmetric, in addition to like the region. Yeah, my bad. So what that means in terms of like row of x, y, and z, where your mass density function has 3 variables in it, if you see that your mass density function is only comprised of x's, like row of x, y, z equals x squared plus 2x plus 8 or something, we know that x is the only variable that affects the density. So we know that it's going to be symmetric about the x-axis. And that makes sense, because for a given x value, all of the values along that plane, like to the side and above it, like moving in the y direction and moving in the z direction, are going to have the same value. So in terms of like three-dimensional symmetry, that's the big hint that you want to look for. All right, so going back to the objectives, compute the center of mass of three-dimensional objects, like that. Moments of inertia, like I said, we didn't really spend that much time on it homework-wise, and you didn't really stress it in class, so I'm just going to go ahead and leave it as, mass times distance squared. Do we have any questions on 15.5? Nope. Okay, cool. So that pretty much concludes chapter 15 because we skipped 15.6 due to all the snow days. So I'm gonna start 16, but let me reset this real quick.